going to be equal to the vector sum of the individual electric fields. Now this is what we learned. Now we said we want to apply this at certain points, and then we said here there's a triangle. There is a charge Q here, there's a charge Q here. We said the electric field at this point P will be EP1 will be KQ by A squared. EP2 will become another KQ by A squared. And then we said the net electric field, which will be EP1 plus EP2. That is the electric field because of 1 and because of 2. Now this is not equal to 2KQ by A squared. This is what we said. Yeah. Why? Because these have to be added like vector quantities. And if these are added like vector quantities, the quantity that you would get here is root 3 KQ upon A squared. So this is what we said. Then we moved on, and then I did slightly difficult questions that I worked with the square. This all of you understood. Then I worked with the hexagon. This is where I gave as a homework. These questions are quite difficult. These are entrance type questions, especially the JEE mains and advanced. So take it up as a challenge and work. Don't say I don't know how to do, because this question won't come again. There will be some other form of this question which you have to learn to understand. Now, if I have to find out the electric field here, this electric field is equal to KQ by 2A squared I cap. This electric field, this angle here is 60 degrees, so cos 60. So I can write that as this is equal to KQ by A squared cos 60 I cap plus sin 60 J cap. Okay, now this one will be cos 60 I cap, and it will become minus sin 60 J cap, right? Then for this one, now for this one, this angle will become 30 degrees. So this will become KQ by 3A, I mean it is root 3A the whole square, again cos 30 sin 30. So now you have those 1, 2, 3, 4, 5 vectors. Now add up the 5 vectors to get the answer. Okay, so that is how you get it. The next one is that about a cube. So here is a cube. This is how it is. Now this will be a little bit more complicated. You will have to imagine there's nothing else that you can do. Look, this is a vector, right? So you can find out the direction of this vector, 45 degrees. Now this will be along I cap or J cap. This will be along I cap or J cap. This will be along I cap or J cap. 3 vectors are very simple. Now this is I, this is J, this is K. This will be along IJ. This will be along JK. So like that you have to write the vectors and then you will have to work it out. This is for you to work out. This question came as 10 marks in a JEE advanced paper. So obviously do not expect that it will be a very, very simple one. So I will leave it as a challenge for you to do it, and then so yeah, so I would leave it for you to work on it and then understand it. So let's move on. Now we are learning about the electric fields. So we want to discuss a little bit more about electric fields and then work. So first understand that this is an electric field here. Now this electric field is going from the east direction, from the west direction towards the east direction, right? Now this electric field and this electric field, there's a difference between these two. Do you see here the lines are denser? So if the lines are denser, this electric field is stronger. Now here the lines are rarer, so this is a weaker electric field. Okay, this is a weaker electric field. Now suppose I have a plane here. Suppose I have a plane here. Here I have a plane. Can you tell me how many field lines are cutting through this plane? If you look at this diagram, obviously there are 0 field lines cutting through this plane. Now this number of field lines which are cutting through a given plane is what is referred to as the electric flux. Yeah. So the electric flux refers to number of field lines cutting through a given plane. So in this case, the number of field lines is 0. So the flux is 0. Yeah. So electric flux refers to the number of field lines cutting through a given plane. But in this, there is a problem. The number of field lines to be drawn is not mathematically defined. Now, to make it mathematically defined, I have a new definition, a mathematical definition for flux. Mathematically, electric flux is equal to E dot A. Yeah. So electric flux is the number of field lines which are cutting through a given cross-sectional area or given cross-sectional plane. Then mathematically, electric flux is equal to E dot A. So if you understand E dot A, it is equal to EA cos theta. Now in this case, I think we made a mistake. Yeah. So this is in the direction, this is parallel to this. So if it is parallel to this, theta is 0. So if theta is 0, flux should be 0. Sorry, if theta is 0, cos theta is not 0. So flux cannot be 0. Right? But here we have to understand, we have not made any mistake. We have to understand that the area vector by definition is perpendicular to the plane. So now if the area vector is perpendicular to the plane, what is the angle between the area vector and the electric field? 90 degrees. So now what does it become? It becomes EA cos 90. And that EA cos 90 will give you 0. Do we understand this? Can we make some notes? Can we write down what is electric flux and what happens here? Then when compared to this, if I have a plane which is in this way, and now I ask what is the flux through this? Definitely it seems to be all of them, but we don't answer it that way. We will answer that the electric flux is equal to EA cos theta. Now this is 90 degrees perpendicular, that's the area vector. So now the area vector and E vector are parallel. So the angle there is 0. So it is equal to EA. So this is how you can find out the electric flux. So when the area is perpendicular, when in this configuration, the flux is maximum. In this configuration, the flux is minimum. Now, suppose I have a coordinate system, suppose, and I have a charge here. Now I'm drawing a sphere. So if I'm drawing a sphere, there are some field lines going this way. There are some field lines here. So how many field lines are cutting through this? 4 field lines are cutting through this. But what is the electric flux? E equal to, so the electric flux will be E into area. What is E? From Coulomb's law, it is KQ by R squared. What is area? Area is 4 pi R squared. Do you see that this R squared gets cancelled? So do you see that the electric flux there is equal to a constant? And it depends K. If I take K, it is 1 by 4 pi epsilon naught. So the 4 pi here gets cancelled. So it is equal to what? Q by epsilon naught. Now this is the basis behind Gauss' law. Okay, what Gauss said is that if you have a charge and if there is a closed body around it, if there is a closed surface around it, the flux through the surface is proportional to Q and is equal to Q by epsilon naught. According to Gauss' law, the flux through a closed surface is proportional to the charge present inside. Charge present inside it. Yeah, and equals Q by epsilon naught. The flux through a closed surface is equal to Q by epsilon naught. Yeah, are you able to understand this? Please make a note, and then we will spend the rest of the day discussing various aspects of this. So the total flux through a closed surface is equal to Q by epsilon naught. Now I would like to take up new cases and then let us work it out. So first case is, I'll go back to the old one again. So if there is a charge Q here, if I draw one surface here and if I draw one surface here, what will be the ratio of the flux through each? Suppose this is R, this is 2R. What will be the ratio of the flux? Flux is equal to E dot A. So students will likely to say that flux 1 is proportional to 4 pi R squared. Flux 2 is proportional to 4 pi 2R the whole square. So phi 1 by phi 2 is equal to 1 upon 4. This is what many students will say it is wrong. Yeah, we have to go back to the definition of flux. The definition of flux is, it is the number of field lines which are cutting. So if there are 4 field lines cutting through this, there will be the same 4 cutting through the other, same 4 cutting to the other, same 4 cutting to the other. So what will be the ratio of flux? Phi 1 by phi 2 is equal to 1. Now this is what I explained to you in another way, saying that phi 1 is proportional to Q by epsilon naught, or is equal to Q by epsilon naught. Phi 2 is also equal to Q by epsilon naught. So what is phi 1 by phi 2 equal to 1? Okay, so this is how you go ahead. Now, if you are understanding this concept, let's look at some more applications. Now here I have an electric field. Okay, so in this electric field, I have kept a square, a cube, sorry, not a square, a cube. My question to you is, come on, let's try to find out what is the flux through this cube. Okay, so let me find out. So let me write this as surface 1. Surface 1, the area vector is in this direction. So the angle is 90. I was explaining to you, the flux here is 0, the flux here is 0, the flux here is 0, and the flux on this side also is 0. But on this side, the area vector is on this side. So flux on 1 plus flux on 2 plus flux on 3 plus flux on 4 plus flux on 5 plus flux on 5 will be E A cos 0 plus flux on the other wall will become E A cos 180. Yeah. So how much is this? 0. How much is this? 0. So how much will be the net? 0. So the total flux through this cube is equal to 0. But the flux through this wall, is equal to E into A. The flux through this wall is minus E into A, such that the net flux is becoming equal to 0. Okay, I hope you guys are able to understand. Yeah, I will tell you few things. When you are preparing for JEE, many people think that just working out problems will work out. No, it doesn't. Now, working problems is possible only after you have learned your theory well. So please spend adequate time trying to learn the theory. It is only the theory which will give rise to an analysis towards a problem. If you don't know theory, there is no way you will be able to analyze a new problem and work. 90% of the problems are there in the market already there. So somebody or the other has seen the solution and they can tell you the solution. But that is not the way you will be able to prepare and do well as far as the NEET is, as far as the JEE is concerned. The only way you will be able to do is when your theoretical base is strong, so that you can look at problems and solve them. Okay, anyway, the next one. Here is a sphere, is a cube, same cube. This time what I have done is I have placed my charge inside the cube. Now my question to you is, what is the flux? Okay, so now my question is, what is the flux? Look, if I place the cube at the center of the, if I place the charge Q at the center, now this charge means what? I can draw field lines like this. So there will be field lines passing through each of those surfaces. Do you understand? So the flux will be the same, whether it is 1, 2, 3, 4, 5 or 6, the flux will be the same. So can I say 6 times the flux? From there, can I say the flux to any one surface will become Q by 6 epsilon naught? Yeah. So this was a question which came as it is. In many exams, it has come. It can come in many more exams. So flux is equal to Q divided by 6 epsilon naught. This is the flux through each of the phase. Now, suppose I shift the charge up. If I shift the charge up, now what happens? Even now, the total flux will still depend upon total charge inside. So the total flux will be equal to 6Q by epsilon naught, no doubt. But now the flux through each surface won't be the same. The flux through the top surface will be more than the flux through the bottom surface. Okay. At this point, I would like to bring a small analogy. Suppose I have a water sprout here. This water sprout is throwing water in all possible directions. Okay. Now I ask you, okay, tell me how much water is it throwing? So what will you do? You're going to cover it up fully and collect the water? See, even if you leave a small space open, you won't get the full water. To get the full water, you have to cover it up fully. Now this is what is flux. So you see some water which is going out or which is hitting the surface, I can consider those to be my flux. Now, whether I take a sphere of this size or whether I take a sphere of this size, the flux will be the same because the water coming out is still the same. Do you understand? And do you understand that the net flux through this will only depend upon the water coming? I can just take it around this point also. Whether I take 1 or 2 or 3, the water content is going to be the same, so the flux is going to be the same. And if there are gaps in your water collection, definitely you will not be able to collect the whole thing. Now, I can also put a square cube here. I can put also a cylinder. So the flux does not depend upon the geometry. Flux depends only on one thing, the amount of water which was coming out of that water sprout. So if you bring the same analogy here, the flux only depends upon the charge, and if the charge up, symmetry is lost, flux through this surface is more than the flux through this surface, but flux through the side walls is still going to be identical, but we cannot say it is going to be the same, it will be different. But still the total flux will be the same. Now, in a particular year, they gave a question where they drew a cube like this, and they cube. Now they are asking what is the flux through the cube. Yeah, they placed a charge at the edge. I placed the charge inside. When I placed the charge inside, I was very clear the flux is equal to Q by epsilon naught. But now they have placed the charge in one of the edges, one of the corners. And now they are asking, tell me what is the flux through this cube. See, field lines will be going in all directions. There's no way I'll be able to draw and then find out the number of field lines here. But what I can do, I can place cubes on this so that I collect all the field lines. So what will I do? I'll place one cube here. This is one cube. I'll place another cube above this. Then I'll place another cube this way. 2, this is 3. Then I'll place one cube here, 4. Then I'll place one cube in front. One cube in front here, cube on top of that, and one cube on top of that. So totally, if I place 8 cubes, recollect solids. So one atom at the end of the cube was shared by how many atoms? I mean, by how many cubes was it shared here? This will also be shared by 8. So the total flux will cube epsilon naught is equal to 8 times the flux through each cube. So the flux through each cube is equal to Q by 8 epsilon naught. The flux through each cube is equal to Q by 8 epsilon naught. So this is how I can find it out. Again, it is all your ability to think which is more important. It doesn't depend on how many problems you do, where you do, and so on. So please train yourself to think. That is what is very, very important. So anyway, we are looking at applications of Gauss law. We are trying to understand Gauss law better. According to Gauss law, summation E dot A is equal to integral over a closed integral over a closed surface. E dot dA is equal to Q by epsilon naught. So this is what we have. This is Gauss law. Now I want to apply this a little bit more and learn a little bit more about this. So this is Q1. This is Q2. This is Q3. And suppose I have Q4. Let me have an imaginary sphere here. Will you agree that at all points on the sphere, EP is equal to E1 plus E2 plus E3 plus E4? That is what is the principle of superposition. Net electric field at any point is the vector sum of individual electric fields. So here I put the vectors if that makes you happy. So the electric field at any point on the sphere is going to be equal to the vector sum of this. But suppose I am doing EP dot dA. What will I be doing? I'll be doing integral E1 plus E2 plus E3 plus E4 dot dA. So this will give me integral E1 dA plus integral E2 dA plus integral E3 dA plus integral E4 dA. And how much is this equal to? This is equal to the charge inside by epsilon, Q3 by epsilon naught. So this is equal to Q3 by epsilon naught. So how much will E1 dA be equal to? The flux due to Q1 will be 0. How much will E2 dA be equal to? The flux due to Q2, that will also be 0, because all these charges are outside the closed sphere, outside the closed sphere. Yeah. Now what is E3 dot dA equal to? Q by Q3 by epsilon naught, because only Q3 is there inside the charge, inside the sphere. So what is T4 dot dA equal to? 0. Do you understand this? That if I draw an imaginary sphere here and I ask you what is the flux because of Q1? 0. What is the flux because of Q4? 0. Flux because of Q3? 0. Because all these charges lie outside. Only if the charge lies inside that geometry, it will give rise to a flux, otherwise it will not. Am I clear? Do you understand this? So if this is understood by you, let's move on and then let's see a few more small things here. I have taken Q1 and I have drawn my field lines. So all these field lines are valid field lines. If all these field lines are there, why is the flux for this charge equal to 0? Because each one of these field lines is cutting it at 2 points. So if one is positive, the other one will be negative. So the net here is 0. The net here is 0. Now this one will have an area vector this way. This will have an area vector this way. So if one is positive, the other one will be negative. So the total will be 0. So the net field lines from Q1 which are cutting stand this. Yeah. So make some notes here. Think about this. So this is what this was asked in a year in an examination in a JEE advanced paper. This was asked. lot of your questions are basically theoretical questions, which only if you understand the theme of those questions which was asked. Okay, so now let's look at a few more applications of Gauss's law. So next I'll take a point charge here. So there's a point charge here. Let this point charge have a charge q. My question to you is this, that at a distance r from it, what is the electric field? We have already learned from Coulomb's law that it is equal to kq by r squared, means it is 1 by 4 pi epsilon naught q by r squared. This is what we have seen. If this is what we have seen, now let's move a little ahead and then see what we get here. So if I apply Gauss law, surface integral E dot dA is equal to q by epsilon naught. This surface here is a Gaussian surface. A Gaussian surface is a surface on which you are applying Gauss law. It's an imaginary surface. You are drawing that surface. You are drawing that surface to apply Gauss law. I have drawn a spherical Gaussian surface. Why have I drawn a spherical Gaussian surface? Only then I will have symmetry. Symmetry means at each point the electric field will be the same. If at each point the electric field is the same, when I perform this integral, I can write this is equal to E integral dA, because E is the same at all points. So I can say that q by epsilon naught is equal to E into 4 pi r squared. That is the surface of a sphere. So from here I can say that E is equal to q upon 4 pi epsilon naught r squared. So friends, what we have done is we have derived Coulomb's law from Gauss law. Yeah, we have derived Coulomb's law from Gauss law. So now you will ask, which is more fundamental? Is Gauss law more fundamental or Coulomb's law more fundamental? Well, Gauss law is more fundamental. In fact, Gauss law is the first of the equations given by Maxwell. So Maxwell gave 4 equations which explain the whole of electromagnetism. In his 4 laws, Gauss law is more fundamental than Coulomb's law, and I hope you have understood this. This is a 2-mark question that you will get in your board exam. Derive Coulomb's law using Gauss law. It can be a part of a 5-mark question, where the first part is what is Gauss law, then derive Coulomb's law. What is electric flux? Derive Coulomb's law using Gauss law. Okay, so I explained to you Gaussian surface. I explained to you why I took spherical, so that I can make my integral easy. Now, some of you may think, sir, I don't know integration. Well, you will never know integration unless you learn it. So you have to learn it. Maths is so. Integration is probably the 4th last or 5th last chapter in your book. So we can't wait till then for you to learn. So you have to learn. Integration means adding up, summing up. So if you have a sphere, you are adding up all the small areas. So the small areas, if you add up, you'll get the total area of a sphere. And what is the total area of a sphere? 4 pi r squared. But please make sure that you are spending some time trying to learn this. It is important for you to learn. Okay, so I hope you have been able to understand this. Next, let us go to one more application where I have taken a sphere. Okay, I have taken a spherical shell, S-P-H-E-R-I-C-A-L, spherical shell. On the spherical shell, I've given a charge Q. So this sphere is charged. Then I am taking inside the sphere, I am asking you, tell me what is the electric field here. So again, I have drawn a symmetric Gaussian surface. So this is the Gaussian surface. a spherical Gaussian surface. Now this Gaussian surface is where I'm going to apply my Gauss law. So according to Gauss law, integral E dot dA is equal to Q by epsilon naught. Yeah, straight. So I'll have E taking outside. Area is 4 pi r squared. So E into 4 pi r squared should be equal to Q by epsilon naught. Can you tell me what is the charge inside this here? 0, because all the charge is outside. So if all the charge is outside, inside there is no charge. So if there is no charge here, what will this be equal to? 0. So what does that mean? It means that E is equal to 0. So here I have proved that the electric field inside a charged shell is equal to 0. The electric field inside a charged shell is equal to 0. So here we have a charged shell and the electric field is 0. Now this is what is referred to as the first shell law, SHELL-LAW. What it means is only if a charge is present inside the Gaussian surface, it will impact the electric field. Any charge outside will not impact the electric field as far as the shell is concerned. Yeah, we have learned the same thing in gravitation. So if you draw a sphere here, this mass, the outer mass, will not affect the gravitational force inside. Only this mass will impact the gravitational force. Same way, only charge which is present inside the shell will give rise to an electrostatic force or an electric field. Charge which is outside will not. Okay, so this is what is referred to as the first shell law. Now let's see what happens outside the shell. This is the shell. This was given a charge Q. Now if you're talking outside the shell, so I have drawn another one. Your question is, so I want to find out. So here it is. So again, Gauss law, E dot dA is equal to Q by epsilon naught. Here Q was capital Q by epsilon naught. Sphere I have drawn, so E is constant. So E into 4 pi r squared is equal to Q by epsilon naught. So I'll say that E is equal to Q by 4 pi what it is. That means for all points outside the shell, the charge behaves as if it is located at the center of the shell. This is the second shell law. So second shell law. Inside the shell, the charge is outside, so there is no electric field. The next one is for all points outside the shell, the charge behaves as if it is located at the center of the shell. Yeah, and the electric field is equal to KQ by R squared. Okay, so I hope again we are able to understand. I'll stop for a minute. Please make a note on shell law 1 and shell law 2. What is shell law 1? What is shell law 2? First, we will learn all the theory. As we learn all the theory, we are working out numericals also. So, okay, so here these are all applications of Gauss law. This question won't come in a NCERT exam, but they can ask you what is the electric field inside a charged shell as a 1-mark question. But these questions come in your board and the other exams, the entrance exams. Applications of these come quite a few times. Applications of these have come. Okay, so if you've understood this, let's go to the next level. So the next level now is I have a conductor. Okay, we can do it in a different way. I don't have to do this. Suppose there's an electric field. Suppose there is an electric field. Now, in the electric field, I taken a conductor. Now, first, what is a conductor? Conductor are those materials which have free electrons. So these free electrons or mobile electrons, they are basically the charge carriers. So they will move around. Now, if I place such a thing in an electric field, the positives, this is the direction of force on the positive. So the electrons will come onto this side and then they will assemble. So if the electrons come on this side and assemble, there will be a deficiency of electrons on the other side. So there are positives on this side. So if there are negatives on one side, positives on one side, now what is going to happen? Now there is going to be an electric field in this direction. There is an external electric field, which I'm giving it as E. There's an electric field inside the conductor. This is going to be equal to the net electric field. Net electric field. Now, as long as there is an electric field, the electrons will be moving. When will the electrons stop moving? When there is no force acting. No force acting means net field is equal to 0. That means what? E is equal to EC. The external field, this field, is equal to the field inside the conductor. So the net force is equal to 0. Do you understand this? So what does it mean? It means that if a conductor is placed in an electric field, charge distribution takes place such that the net electric field inside the conductor is 0. Yes, suppose E comes because of a charge Q and is equal to Q by 4 pi epsilon naught R squared. Then the electric field inside the conductor should be Q divided by 4 pi epsilon naught into ER into R squared. Now we are seeing this is equal to 0. This is not 0. These are definitely not 0. This is also not 0. This is also not anything. So what is the issue? Why did it become 0? It became 0 because ER is equal to infinity. So this is a very, very, very important concept, that there cannot be an electric field. There cannot be an electric field inside a conductor. There cannot be an electric field inside the conductor. In other words, the dielectric constant or the relative permittivity of a conductor is infinity. The relative permittivity of a conductor is infinity. Yeah. Then now we can ask, how will the other materials behave? So I have an electric field here. I placed a dielectric of dielectric constant K. Now when a dielectric of dielectric constant K is placed, see, dielectric is made up of atoms and molecules. Every atom has a nucleus and then it has its electrons. So now because of the electric kind of get disturbed and go this side. Earlier, when I had the nucleus and the atom, the nucleus was here and the atom was here. The charge centers were the same. So I could say an atom is neutral. I'm perfect with it. Now, the moment I placed it in an external field, the positives got deviated a little to the right and the negatives were there. Positives, negatives, positive, negatives, positive, negatives. Ultimately, it will look something like this. So there are some positives on this side, there are some negatives on this side. The net electric field is equal to the external field minus the electric field due to the dielectric. Do you understand? Now this separation of the positive center and the electrons in a material is what is referred to as polarization. So when a dielectric is placed inside a conductor, polarization takes place. Because of polarization, there is a shift in the positive and the negative charge density, charge centers. So positive charge centers are here, negative charge centers are here. So if positive charge centers are here, negative charge centers are here, there is a slight electric field going from the right towards the left. That is the electric field inside the dielectric. And the net electric field is E minus ET. Now, suppose this electric field was because of some charge Q. Can I say that E minus ED is equal to Q by 4 pi epsilon naught ER R squared? This is nothing but E by K, the dielectric constant, ER, I'm sorry, not K, ER, E by ER. So, E minus ED is equal to E by ER, which we can also write it as E by K. So, here I can say that ED is equal to E into 1 minus 1 by K. That means if the external field is E, the field because of polarization in the dielectric is equal to this much. This was a question which came in a JEE mains paper. Okay. Then what is the net field inside the dielectric? The net field inside the dielectric is E by K. That's what we said. When we added a salt to water, we said because of the dielectric force, water gets separated. If we didn't do it, I'll explain it to you now. Okay, so if there is an electric field E and if you place a medium, the electric field inside the medium becomes E by K. So do you see that the electric fields have become weaker? In any medium, the electric field will become weaker. This K is what is referred to as the dielectric constant, also referred to as relative permittivity. According to Coulomb's law, F is equal to K Q1 Q2 by R squared, where K is equal to 1 by 4 pi epsilon naught. If you place this in vacuum, if you place this in a medium, according to Coulomb's law, F is equal to 1 by 4 pi epsilon naught into ER into Q1 Q2 by R squared. That means in any medium, force becomes force in vacuum divided by ER. ER is a constant called relative permittivity. Relative permittivity. The permittivity of free space is E naught. The permittivity for any other medium is ER into E naught. This is for any other medium. So the force in any medium is equal to this much. So let me see, force in vacuum divided by force in medium is equal to K Q1 Q2 by R squared divided by K Q divided by K Q1 Q2 by epsilon naught into ER into R squared. All these gets cancelled. This goes up and this is ER, also called as K, the dielectric constant. This is capital K, this is small k. So FV by K is equal to Fm. K is called the dielectric constant, also referred to as relative permittivity. Please make notes so that you are able to understand. The definition of relative permittivity is the ratio of the force in vacuum to the force in any medium, or force in any medium by a constant is equal to the force in vacuum by a constant is equal to force in any medium. Now, okay, first you make a note. I'll wait for a second. You guys make a note, and then we will move. Okay, so if you get it, great. So I spoke about relative permittivity. So the specific thing I was telling you is this. Suppose we take NaCl. Okay, NaCl is an electrovalent compound. So you have Na plus and you have Cl minus. So there is a strong electrostatic force between them. It is that strong electrostatic force between them which puts them together. So that force will become equal to 1 by 4 pi epsilon naught Q1 Q2 by R square. That is equal to the force. Now suppose I add it in water. Suppose I add it in water. Now in water, what will happen? The force will become 1 by K times 1 by 4 pi epsilon naught. K for water, I am telling you, is 80. What does it mean? It means that the electrostatic force inside water have become 80 times less than what it was in air. So if it has become 80 times, that means now separating the ions would become easy. So this is what water does. Water is able to separate the ions. And that is why we say that NaCl interacts with water to form Na aqueous plus Na plus aqueous plus Cl minus aqueous. And so NaCl is soluble in water. Solubility of any salt means simple separation of ions. And why does it happen? Because of the high dielectric constant of water. Now, I have told you that conductors have an infinite dielectric constant. Vacuum has dielectric constant 1. Water has dielectric constant 80. Now, can you tell me what kind of materials will have dielectric constant on this side and what type of materials will have dielectric constant on this side? Can I say greater the polar nature, greater is the dielectric constant? If something has less polar nature, it will have less dielectric constant. So I can, in a physics exam, I can ask you a question. Suppose I have CH3OH, C2H5OH, and H2O. I can ask you to arrange them in increasing order of dielectric constant. So H2O here, because of the 2 bonds, this will definitely have maximum polarity. Now CH3 is electron releasing group. So O, CH3 here, here H. This is an electron releasing group here. So the dipole moment here will be less than the dipole moment here. Now C2H5 is an even better electron releasing group. So it's a better electron releasing group means dipole moment will be even lesser. So which will have the least dielectric constant? C2H5OH will have the least dielectric constant, followed by CH3OH. followed by H2O, right? So here we have applied the logic that we are learning to identify something. Now this is what is physics. These are the kinds of logics that you will have to develop to crack the JEE mains. Okay, so work with yourself, work well, you will get it. Okay, so I am still to do a lot of applications of Gauss law. We will spend tomorrow there is no class. We will spend a Monday again talking about Gauss law. So yeah, I am done for the day. If you all have any doubts, anything, Vishnu will guide you. Please let me know. I'll be happy to show. What we did today is this. We started off by talking about electric field. Somebody had asked me yesterday, why is it F by dq? So I explained that. Then I explained this hexagon question. Then before that, I think I explained to you the triangle question and it got deleted. Then I explained to you the hexagon question, how to work it out. Then I told you to work it out by yourself. I discussed briefly the cube question. Again, try to work it out. Take as much time, but try to work it out by yourself. There is no fun in getting a solution from someone. Then I explained to you electric flux. I explained to you the area vector. I explained to you that here the flux is maximum, here the flux is minimum. Then I gave you the definition of what is electric flux. Then I discussed Gauss law. I intuitively explained to you how to derive Gauss law, how to think about Gauss law. So Gauss law is equal to the net flux through a closed surface is equal to Q by epsilon naught. So that is how you get Gauss law. Then we worked a little bit more, and then I explained to you how the flux through two surfaces is not 1:4, but it is equal to 1:1, because flux is nothing but number of field lines cutting. Then I took a cube, placed it in an external field, and then we found out that the net flux was 0. The net flux is 0 because there is no charge inside. Only if there is charge inside will there be a flux. Then I took a charge at the center, and then we found out the flux per unit surface. Then I explained to you what if the charge is placed at the boundary. I said it is Q by 8 epsilon naught. You'll have to think and come back. Then I explained to you flux is just like water coming out of a nozzle, and you want to collect all the water. What will you do? So you can have a sphere around the nozzle, you can have the square around the nozzle, you can have the cylinder around the nozzle. But only if you have a curved surface, you can collect closed surface, you can collect water. Otherwise, you won't be able to collect any water. So that is what I was trying to explain to you. Then we took 4 different charges, and I explained to you how the electric field is the vector sum, but the flux depends only on the charge which is present inside. So some of these integrals were 0. In a particular exam, for a similar diagram, they asked what is E dot dA equal to, and that is equal to 0. Then we have this, we have a Gaussian surface, and then we have a spherical Gaussian surface, and kq by r squared we applied, and I tried to derive Coulomb's law by using Gauss law. And then we saw that Gauss law is more fundamental than Coulomb's law. And then I explained this to you. Then I explained to you shell law, first shell law, that the net electric field inside the charged shell is 0. Then I derived that by using Gauss law. I did the same for outside the shell, and then we found that out. We took a detour, then we applied, we put a conductor in an external field, found out that Q electric field is 0. My next thing would be that I would take a conductor which is charged and show to you that the electric field inside it is 0. So I thought I would do that first and then come here. In the other class, I did this first and then went there. So it's the same thing. So I just wanted to communicate what happens inside a dielectric. So that is what we did here. Okay. So I will continue from here in the next class on Monday, and we will do more applications. Monday also, we are only going to look at Gauss law, nothing more than that. Okay. So please read and come. Only if you read, you'll understand. Otherwise, you won't. Physics is not something, I don't have any injection that I give it to you and all of you become great in physics. No. But you have the injection in your hand. If you work on it, you will be able to solve your problems and you will be able to come out successful. So that's it. Best wishes to you all. I'll stop here. See you on Monday.